In this video we're going to look at the calculus, that is the differentiation and the integration associated with the inverse trigonometric functions. Now, because we're dealing with differentiation and integration, it is critical that throughout this video we are using radians as our angular measure. So there shouldn't be any use of degrees in this video. So, in Unit 3 of the Mathematics A-Level, you met for the first time the inverse trig functions, namely sine to the minus 1 of x, cos to the minus 1 of x, and tan to the minus 1 of x. And we'll have seen that the graph of sine to the minus 1 of x looks like this. What we now want to do is we want to discover the gradient of this graph. So we want to learn how to differentiate sine to the minus 1 of x. So if we've got y equals sine to minus 1 of x, then that certainly means that we've got sine y is equal to x. And we can differentiate this expression implicitly with respect to x to obtain cos y dy by dx equals 1. In other words, dy by dx is 1 over cos y. However, we would really want to have dy by dx to be in terms of x and not in terms of y. We do know that cos squared y plus sine squared y is equal to 1. So that tells me that cos y is plus or minus the square root of 1 minus sine squared y. But sine y is x. So we can say that cos y is plus or minus the square root of 1 minus x squared. So we've got dy by dx is 1 over plus or minus the square root of 1 minus x squared. But if we look at the graph of y equals sine to the minus 1 of x, we can see that it's an increasing function, which means that its gradient must be positive everywhere. So we want the positive square root. So we can now say that dy by dx is 1 over the square root of 1 minus x squared. We can do an entirely similar thing for cos to the minus 1 of x. So we've got the graph of y equals cos to the minus 1 of x. If y is cos to the minus 1 of x, then we've got cos y is equal to x, which means if I differentiate implicitly, I obtain minus sine y dy by dx equals 1. Which means that I've got dy by dx is minus 1 over sine y. Now again, we want to get rid of dy by dx being in terms of y and obtain an expression for dy by dx in terms of x. We know though that cos squared y plus sine squared y is 1, so sine y is plus or minus the square root of 1 minus cos squared y. And we know that cos y is x, so we can say that sine y is plus or minus the square root of 1 minus x squared. So that now gives me dy by dx is minus 1 over plus or minus the square root of 1 minus x squared. From the graph, we can see that the gradient of y equals cos to the minus 1 of x is always negative. So that means that I need dy by dx to be negative. Well, minus 1 is a negative number, so I need the denominator of the fraction to be positive. So I'm going to take the positive square root here. So I've got dy by dx is minus 1 over the square root of 1 minus x squared. For the next result, we're going to look at y equals tan to the minus 1 of x. I mean, you can see what its graph looks like. If we've got y equals tan to the minus 1 of x, then that is the same thing as saying tan y is equal to x. Again, we're going to differentiate this with respect to x, which will require implicit differentiation. Derivative of tan is sec squared, so we've got sec squared y dy by dx must equal 1. In other words, dy by dx is 1 over sec squared y. But we know that sec squared y is the same thing as tan squared y plus 1. And we also know that tan y is x. So we've got sec squared y is the same thing as x squared plus 1. So we've got dy by dx is 1 over x squared plus 1. So we've got here example 1, which is just a straight differentiation example. We've got to differentiate, first of all, tan to the minus 1 of 3x squared. Well, if I have y equals tan to the minus 1 of 3x squared, that is the same thing as tan to the minus 1 of u, where u is equal to 3x squared. So using the chain rule, I've got dy by dx is du by dx times by dy by du. Du by dx is 6x. dy by du, well, y is tan to the minus 1 of u, so dy by du is going to be 1 over 1 plus u squared. So I've got dy by dx is 6x times by 1 over 1 plus u squared, but u is 3x squared. So I've got 6x times by 1 over 1 plus 3x squared squared. In other words, I've got 6x over 1 plus 9x to the power 4. For the second example I've got to differentiate is x cubed sine to the minus 1 of 2x. So this is going to be using the product rule with u equals x cubed and v equals sine to the minus 1 of 2x. In which case I can certainly say that du by dx is 3x squared. To differentiate v, I'm going to need to use the chain rule. So v is sine to the minus 1 of 2x. The derivative of 2x is just 2. The derivative of sine to the minus 1 of something with respect to the something is 1 over the square root of 1 minus the something squared. So dv by dx is going to be 2 times by 1 over the square root of 1 minus 2x squared, which is the chain rule. In other words, it's going to be 2 over the root of 1 minus 4x squared. So now applying the product rule, I'm going to have dy by dx is 3x squared sine to the minus 1 of 2x plus x cubed times by 2 over root of 1 minus 4x squared, which can of course be rewritten as 3x squared sine to the minus 1 of 2x plus 2x cubed over the square root of 1 minus 4x squared. Moving on to the final example, we're going to need to use the quotient rule with u equals tan to the minus 1 of x and v equals 1 plus x. So du by dx is 1 over 1 plus x squared. dv by dx is just equal to 1. And using the quotient rule to differentiate u over v, we obtain du by dx times v minus u dv by dx all over v squared. So du by dx is 1 over 1 plus x squared times by v is 1 plus x minus u tan to the minus 1 of x times by 1 all over 1 plus x all squared. That's the v squared. If we multiply the top and the bottom by 1 plus x squared, then we obtain 1 plus x minus 1 plus x squared times 10 to the minus 1 of x, all divided by 1 plus x all squared times by 1 plus x squared. Moving on to a second example, we want to find the stationary points on the graph of y equals x minus 5 tan to the minus 1 of 2x. So we need to differentiate, and if we use the chain rule to differentiate tan to the minus 1 of 2x, we obtain the derivative as being 2 times 1 over 1 plus 2x squared. In other words, 2 over 1 plus 4x squared. So we can now write down the gradient of our curve. So we've got dy by dx is 1 minus 10 over 1 plus 4x squared. For a stationary point, we need dy by dx to equal 0. So we've got 1 minus 10 over 1 plus 4x squared must equal 0. So that gives me 1 plus 4x squared must equal 10. So x squared must be 9 over 4. Or x is plus or minus 3 upon 2. So we've got our stationary points are 3 over 2 minus 5 tan to the minus 1 of 3, or minus 3 upon 2, minus 3 upon 2, take away tan to the minus 1 of minus 3. Or approximately the stationary points are 1.5 minus 4.745, or minus 1.5, 4.745. Right, so now I want to just consider the derivative of sine to the minus 1 of x over a. Using the chain rule then, we can say that sine to the minus 1 of x over a is sine to the minus 1 of u, where u is x upon a, or in other words 1 over a times by x. So dy by dx is du by dx times by dy by du. Du by dx is just 1 over a. Dy by du is 1 over the root of 1 minus u squared. I know that u is x over a, so that's 1 over a times by 1 over the root of 1 minus x upon a squared. Now, 1 upon a is the same thing as 1 over the root of a squared. So I've got 1 over root of a squared times by 1 over the square root of 1 minus x squared over a squared. Now if I multiply out the bottoms, I'm going to obtain 1 over the root of a squared minus x squared. So if we've got y equals sine to the minus 1 of x over a, then dy by dx is 1 over the root of a squared minus x squared. And we'll see that this result is very useful, particularly actually as an integration result rather than a differentiation result. We're also going to consider y equals tan to the minus 1 of x over a. So again, this can be differentiated using the chain rule. We can say that y is tan to the minus 1 of u, where u equals x over a. So dy by dx is du by dx times by dy by du. Du by dx is 1 over a. Dy by du is going to be 1 over u squared plus 1. So remembering that u is x over a, I can say that this is 1 over a times by x over a all squared plus 1. which is the same thing. Now 1 over a is the same thing as a over a squared, times by 1 over x squared upon a squared, add 1, which gives me a over x squared plus a squared. So we've got, if y equals tan to the minus 1 of x upon a, then dy by dx is a over x squared plus a squared. So we've now encountered 4 different differentiation results, which I want to recall at this stage. If y is sine to the minus 1 of x, then dy by dx is 1 over the root of 1 minus x squared. If y is sine to the minus 1 of x upon a, then dy by dx is 1 over the root of a squared minus x squared. If y is tan to the minus 1 of x, then dy by dx is 1 over 1 plus x squared. And if y is tan to the minus 1 of x upon a, then dy by dx is a upon a squared plus x squared. Now these 4 differentiation results give us very quickly 4 very useful integration results. So the first one is that the integral of 1 over root 1 minus x squared is sine to the minus 1 over x plus c. We've also got the integral of 1 over the root of a squared minus x squared is sine to the minus 1 of x upon a plus a constant. We've also got the integral of 1 over 1 plus x squared is tan to the minus 1 of x plus a constant. And final result here is the integral of 1 over a squared plus x squared is 1 over a tan to the minus 1 of x over a. Now notice the 1 over a in front of the tan to the minus 1 of x over a here. Why is that there? Well, we know that if y is tan to the minus 1 of x over a, then dy by dx is a over a squared plus x squared. So if y is 1 over a tan to the minus 1 of x over a, dy by dx will be 1 over a squared plus x squared. So that's now telling me that the integral of 1 over a squared plus x squared is going to be 1 over a tan to the minus 1 of x upon a plus the constant. So we've got those 4 standard integral results, and they're immensely useful results to have. So let's have a look at using these results. So first of all, let's have the integral between 0 and 5 of 1 over 25 plus x squared. Well, we can just use the fourth of our 4 results above with a equals 5 and say that we've got 1/5 tan to the minus 1 of x over 5 as the integral of 1 over 25 plus x squared. So we've got limits of 0 and 5. So we've got 1/5 tan to the minus 1 of 1. Take away 1/5 tan to the minus 1 of 0. Now we know that 1 is the tangent of 45 degrees, but we've got to remember in this video that we're using radians and not degrees. So 1 is the tangent of pi by 4 radians. So we've got 1/5 times by pi by 4. Take away 1/5 of tan to the minus 1 of 0. Tan to the minus 1 of 0 is 0. So we've got 1/5 of pi by 4. Take away 1/5 of 0, which gives me pi by 20. If I've got the integral of 3 over 4 plus x squared, well, that is the same thing as 3 times by the integral of 1 over 4 plus x squared. So using my fourth result again, this time with a equals 2, I can say I've got 3 times by a half of tan to the minus 1 of x upon 2 plus a constant. In other words, 3 over 2 tan to the minus 1 of x over 2 plus a constant. Integral between 0 and 3 of 1 over the root of 36 minus x squared. Well, using the second of our four results above, with a equals 6, I can say that the integral of 1 over root 36 minus x squared is sine to the minus 1 of x over 6. So I need the value of sine to the minus 1 of x over 6 when x is 3, take away the value of sine to the minus 1 of x over 6 when x is 0. So that is sine to the minus 1 of a half, take away sine to the minus 1 of 0. Now we know the angle with a sine of a half is 30 degrees, but again we must remember to be using radians, and sine to the minus 1 of a half in radians is pi by 6. And sine to the minus 1 of 0 is 0. So we've got pi by 6, take away 0, which gives me pi by 6. For the next one, it looks slightly more awkward. I've got the integral of 1 over the square root of 25 minus 9x squared. Now this resembles most closely the second of our four standard integrals at the top of the page, but we don't really like that 9 in front of the x squared. So what we're going to do is we're simply going to factor the 9 out carefully. So I could say that what I've got is the integral of 1 over the square root of 9 lots of 25 over 9 minus x squared. I can pull the 9 out of the square root, which now gives me 1 over 3 times the square root of 25 over 9 minus x squared. In other words, I've got 1/3 of the integral of 1 over root 25 over 9 minus x squared. Now that is just like the second integral at the top of the page, where a equals 5 upon 3. So I can say the integral is going to be 1/3 sine to the minus 1 of x upon a, that is x upon 5 upon 3. And that simplifies a little bit to give me 1/3 sine to the minus 1 of 3x over 5 plus the constant. Okay, a few more examples like this. Now we've got the integral of 5 over 16 plus 81 lots of x squared to do. Now this looks like the fourth of our standard integrals at the top of the page, except we've got that 81 in front of the x squared, which we really don't want. And we're going to do very much the same as we did in the previous example. We're going to factor out the 81. So I can say that's the same thing as the integral of 5 over 81 lots of 16 over 81 add x squared. I could take the 5 over 81 outside the integral sign. So I've got 5 over 81 times by the integral of 1 over 16 81sts plus x squared. I can now use the fourth result where a equals 4 over 9. So that's going to give me 5 81sts times by 1 over a, and a was 4 over 9. So I've got 5 81sts times 1 over 4 ninths, tan to the minus 1 of x over a, which is 4/9. So we've got 5/81 times 1 over 4/9 tan to the minus 1 of x over 4/9 plus c. And if we simplify that out, we've got 5/36 tan to the minus 1 of 9x over 4 plus c. Now the final example is a bit of a hybrid example. We've got the integral between 0 and 3 of 6x plus 5 over x squared plus 9. I'm certainly allowed to rewrite that as being the integral of 6x over x squared plus 9 plus 5 over x squared plus 9. Now 6x over x squared plus 9 is very similar to some of the integrals that you will have met in Unit 3 of your mathematics, where the top is almost the derivative of the bottom. Indeed, if we say that 6x over x squared plus 9 is the same thing as 3 times 2x over x squared plus 9, then 2x over x squared plus 9, we are in exactly the position where the top is the derivative of the bottom. So the integral of 2x over x squared plus 9 is the natural logarithm of x squared plus 9. The 5 over x squared plus 9 that we've got, we can certainly say is the same thing as 5 times 1 over x squared plus 9, and we can certainly handle that using the fourth of the results at the top of the page. So we can say that the integral of 3 times 2x over x squared plus 9 plus 5 times 1 over x squared plus 9 is going to be 3 times the logarithm of x squared plus 9 plus 5 times by a third tan to the minus 1 of x upon 3. And I need the value of that expression when x is 3, take away the value of that expression when x equals 0. So substituting in x equals 3, I'm going to get 3 times the logarithm of 18 plus 5 upon 3 tan to the minus 1 of 0, which is 3 log 18 plus 5 over 3 times by pi by 4. Then I've got to take away the expression when I substitute in x equals 0, which is going to be 3 logarithm of 9 plus 5 over 3 tan to the minus 1 of 0, but tan to the minus 1 of 0 is 0. So as a final answer, we've got 3 logarithm 18, take away 3 logarithm of 9, which simplifies to 3 logarithm of 2, plus 5 pi divided by 12. And for our final example in this video, we're going to look at the function f, which is defined by 4x squared plus x plus 12 divided by x squared plus 9 times by x plus 2. We're going to write f as a sum of partial fractions, and we're going to then evaluate the integral between 0 and 3 of f. Now we've in fact done this example with partial fractions in an earlier video, and we saw that 4x squared plus x plus 12 over x squared plus 9 times by x plus 2 can be written as 2x minus 3 over x squared plus 9 plus 2 over x plus 2. If that's a little bit hazy at this stage, I would suggest you go back and review the partial fractions video from this series of videos. So we can now say then the integral between 0 and 3 of f of x is actually equal to the integral between 0 and 3 of 2x minus 3 over x squared plus 9 plus 2 over x plus 2. We can split the 2x minus 3 over x squared plus 9 into 2x over x squared plus 9, take away 3 times 1 over x squared plus 9, plus 2 times by 1 over x plus 2. And each of those terms we should be able to integrate. 2x over x squared plus 9 is a standard integral where we've got the top being the derivative of the bottom, so that is simply going to give me the logarithm of x squared plus 9. 1 over x squared plus 9, again, is a standard integral. It's the one we've been working on this video. The integral of 1 over x squared plus 9 is 1 over 3 tan to the minus 1 of x over 3. So the integral of 3 times 1 over x plus 9 is going to be 3 times a third tan to the minus 1 of x over 3. And finally, 1 over x plus 2 is another case where we have the derivative 1 sitting on top of the function x plus 2. So that tells me that the integral of 1 over x plus 2 is simply the logarithm of x plus 2. So the integral of 2 times 1 over x plus 2 is going to be 2 times the logarithm of x plus 2. So my integration of f of x is logarithm of x squared plus 9, take away tan to the minus 1 of x upon 3, plus 2 times the logarithm of x plus 2. So I've got need to insert the value x equals 3 into that expression and then subtract the value when I insert x equals 0 into that expression. So I've got natural logarithm of 18, take away tan to the minus 1 of 1, add 2 times the logarithm of 5. Then I've got to take away the logarithm of 9 minus tan to the minus 1 of 0 plus 2 log 2. The first bracket simplifies to the logarithm of 18 minus pi by 4 plus 2 log 5, whilst the second bracket simplifies to the logarithm of 9, take away 0 plus 2 ln 2. Using the laws of logarithms, for the first bracket, 2 logarithm 5 is the same thing as the logarithm of 5 squared, in other words the logarithm of 25. The logarithm of 18 plus the logarithm of 25 is the logarithm of 18 times 25, which is the logarithm of 450. So the first bracket simplifies to the logarithm of 450, take away pi by 4. In the second bracket, the logarithm of 9 plus the 2 logarithm of 2 is the same thing as the logarithm of 9 plus the logarithm of 2 squared. In other words, the logarithm of 9 plus the logarithm of 4, which is the logarithm of 36. So our expression we've got at the moment for the integral simplifies to logarithm of 450, take away pi by 4, take away the logarithm of 36. The logarithm of 450, take away the logarithm of 36, is the logarithm of 450 divided by 36, which simplifies to 25 over 2. So my final answer for this integral is the logarithm of 25 over 2, take away pi by 4. And that concludes our video looking at the calculus of and using the inverse trigonometric functions.